Yep.
Hi, everybody. Thanks very much for attending this talk. It's an absolute pleasure to have Moshe Vardi join us for this talk. Many of you may have heard of Moshe Vardi, but if you haven't, he's a professor at Rice University, but he's worked in a very broad range of topics, starting from database theory and automator theory, moving on to temporal logics, or perhaps overlapping quite substantially with temporal logics. And he continues to be interested in those aspects of theoretical computer science, but as and from a community perspective, because of his role for a while as the editor of CACM, he had a number of influential blog posts that kind of challenged certain narratives about computer science and its impact. And I think this talk perhaps is again going back to that kind of political dimension of what it means to work in computer science, both as a scientist and potentially as an end user. So again, we're very happy to have Moshe on this on the Turing virtual seminar. As I just mentioned a few minutes ago, we've been running this for a while now, almost 3 years. We took a short break earlier this year to kind of work out what the future of these talks could look like. So hopefully we'll make these more interactive and allow a chance for people to pose questions, and then we can follow up with these questions later on. Having said that, Moshe, please take it away. Thanks so much for joining us.
Thank you very much for inviting me. So I want to discuss with you today the issue, it's a question mark, a paradigm shift in computer science. Is there a paradigm shift in computer science? So there is a sense that there is something fundamental changing, okay? We are in a peak hype about AI and machine learning. That's the word you hear now every day. You open the newspaper, in the news, everywhere. That's what you hear. And so there is a perception what we are undergoing is what I would say is a Kuhnian paradigm shift. So if you don't know what Kuhnian means, then Thomas Kuhn in the early 60s wrote a paper on the structure of scientific revolution, and he coined the phrase paradigm shift. And that refers to when there is a paradigm shift in science. Suddenly there is a complete fundamental change in how we think about the world, for example. You throw out the old paradigm, you bring the new one. And the poster child for this is how we went from the geocentric model, where the Earth is in the center and everything revolves around the Earth, to the heliocentric model, where all the planets revolve around the sun. And ultimately, in fact, now we know that we live on an insignificant planet next to an insignificant sun, next to an insignificant galaxy in a huge universe. Okay, that was kind of the change. It's the classical paradigm shift. And so there is a sense that something similar is happening in computer science, total paradigm shift. Just to give an example, we started a new degree program at Rice University. And now we have, in addition to have a bachelor degree in computer science, we have a bachelor degree in AI. And there was a huge argument whether the bachelor in AI needs a course in algorithms. And I've argued, yes, we still need algorithms, but I lost the argument. The Bachelor of AI now does not include algorithms. So that's an example of a paradigm shift. But to give a more significant example, I think is what happened with protein folding. So proteins are the building blocks of life. Okay, this we understand today that all of life is a result of working proteins. And therefore, we'd like to understand, it turned out the functionality of the protein is a function of their structure. But structure is hard to determine. We can it's easier to determine the sequence of amino acids, but the actual structure, how it folds, is difficult. You have to do a lot of experimental work. And so far we have been able to determine the structure of about 100,000 proteins, which is a tiny fraction of the world of proteins. And this was known a very, very difficult computational problem. And then AlphaFold came up with using machine learning approach, and he was able to crack the problem and to show it is accuracy is compatible with experimental methods, and it is vastly faster than any other method. And the amazing thing was the Nature paper appeared in 2021, and the Nobel Prize in Chemistry went to Demis Hassabis in 2024. Within 3 years, it was such a revolutionary progress. And unlike the Nobel Prize in physics for Jeff Hinton, and many people question, nobody questioned the Nobel Prize in chemistry for Demis Hassabis. So that's an example of paradigm shift. And indeed, in October 2024, just about a year ago, Vasant Dar published an article in CSCM calling the paradigm shifts in AI. He said the current general AI has reached a major barrier where machine can learn through self-supervision, transform an iPhone application to general purpose technology, like electricity, that would enable the rapid development of transformative application across the economy. For the first time, he wrote, we can converse with an entity, however imperfectly, about anything, as we do with other humans. So he called it paradigm shift. But I'm not a fan of the paradigm of paradigm shift. And let me explain why. So yes, indeed, I think what happened in machine learning in the past decade plus is really revolutionary. Deep learning, LLM, this is really revolutionary. But in reality, I think the paradigm of paradigm shift has been kind of exaggerated to some extent. Yes, in the case of the heliocentric model and the geocentric model, indeed, we threw away the old paradigm to replace by a new one. But this rarely happens. This is just like one example where we throw away the old one. Think what happened with physics, for example. We had Newtonian mechanics, and then we had quantum mechanics and general relativity. But we did not throw away Newtonian mechanics. How did we go to the moon? It's purely classical physics, Newtonian mechanics. And in fact, we think today is the general relativity and quantum mechanics, they refine Newtonian mechanics. They do not throw it away. And my thesis is the same thing, the data-driven science, refine model-driven science, but it does not replace it. We still need model-driven science. And that's the case I will try to make here. And to do that, I'll start talking about the can LLM reason? This is a question that you find lots of discussions today. Can LLM reason? And about a year ago, a paper appeared by Farhat Taj Bar et al. And they question whether LLMs can reason. We found no evidence of formal reasoning in language models. Their behavior is better explained by sophisticated pattern matching. So fragile, in fact, that changing names can alter result by 10%. Kind of here is a bit of a funny example. Question, ChatGPT 01 preview. How many times in my life can I subtract 5 from 35? And ChatGPT says you can subtract 5 from 35 only once in your life. After you subtract 5 from 35, the number is no longer 35, but 30. And it's obvious that the analogy is to the classical Greek kind of parable is you can never dip twice in a river, in the same river, because the river has changed and you have changed. So you cannot subtract 5 from 35 more than once because the numbers have changed. And of course, we all think this is very funny, but it shows that there's no reasoning really. There's more pattern matching than actual reasoning. In fact, Melanie Mitchell in 2023 wrote an article, Can Large Language Model Reason? And she said, while LLMs are not explicitly trained to reason, they exhibit emergent behavior that sometimes look like reasoning. But I have a more fundamental question. Why should we try to get LLM to reasons? LLMs are very good at language. Why should we try to get them to reason? We have deep solvers that excel in reasoning. I'll talk about them. You know, I have a washing machine and I have a dryer. I don't try to wash my clothes in the dryer. I'm not expecting, the washing machine is good for washing. The dryer is good for drying. We should get used tools for what they're good at. The question is, how do we integrate them? In the case of the washer and the dryer, I have to take the clothes out of the washer, move them to the dryer. Maybe someone can automate that. So how do we integrate learning and reasoning? To me, that is the fundamental question, not can LLM reason. And the reason we want to integrate learning and reasoning is because we do it. Daniel Kahneman wrote a book in 2011, Thinking Fast and Slow. And amazingly, this was a year before the deep learning revolution kind of exploded on the scene. But in reality, fast thinking is really machine learning. Okay, so when I drive and I see a stop sign, I have to recognize it's a stop sign, and I do it in very, very fast. Okay, I see a hand in the air or a hand on the sign, it's a stop sign. That's that's learning. That's fast thinking. Slow thinking is learning the rules that you have to stop at the stop sign. Now that might be simple, but then the United States, the traffic light system is complicated. You know, sometimes you have flashing green, which means observe before you turn, things like that. So this is slow thinking, and slow thinking is really logic. That's reasoning, and that's why we need both learning and reasoning. Now, a very nice demonstration of that was a paper by Amnon Shashua, a well-known machine vision person, who wrote about autonomous vehicle in 2017. And he said, if you only want to use machine learning, he argued, we'll have to drive about 1 billion miles. And that may not be practical, he argued in 2017. And he said, why don't we instead combine models and data, and then we should be able to learn the same, we should be able to get to the same safety level in 1 million miles. Well, since then, actually, Tesla figured out how to get 1 billion miles driven. Every Tesla learns, and it communicates with Tesla. The car communicates with Tesla. So now we have some kind of a distributed learning, and maybe this way we'll get to 1 billion miles. But the idea is we'll be better off by combining learning and reasoning, because that's what human beings do. The other argument have to do with the automated decision systems. So in 2018, Jim Laros and Chris Hassing wrote in CSCM about ADS, automated decision systems. And they wrote the widespread adoption of AD systems will be economically disruptive and will raise new complex societal challenges. Disdain for regulation, they said, is pervasive throughout the tech industry. In the case of automated decision making, that would be mistaken. We'll have machine making important decision of impact on human lives. And the question is how to regulate them. And so the common acronym there is FATE, fairness, accountability, transparency, explainability. But how do we explain things to human beings? We have to talk to human beings in their language. And the language of human being is logic. Logic, after all, comes from words. Logic captures how human beings reason. The explanation must be high level rather than low level. So we have to integrate learning with reasoning. So let's go to the modern birth of reasoning. And this is George Boole. And the question that came out of George Boole's work is a decision problem. You are given a Boolean expression using and, or, and not. So the variable are Boolean variables. They can be assigned 0 or 1. And the question here, can you satisfy it? And what it means here, assign 0 and 1 to the x1, x2, and x3, and x4, such that the whole thing will evaluate to 1. And here there is a solution. You can see that if x1 and 2 are 0 and x3 and x4 are 1, this will be evaluated to 1. For variable, it means you have 2 to the 4 equals 16 possibility. That's easy to do on a sheet of paper. What happens if you have 40? What happens if you have 4 million? How do we solve such questions? So already in the 19th century, people start thinking about it. William Stanley Jevons, who was a follower of George Boole, I've given much attention, therefore, to both lessening both the manual and the mental labor of the process of Boolean reasoning. I shall describe several devices which may be adopted for saving trouble and risk of mistake. And in fact, he built the first a logic machine. It's the shape of a piano. It's called logic piano. And it could solve problem with 4 propositions. But in fairness, don't make fun of him. It was done only using moving wooden pieces, so not so trivial. The next quote I find absolutely amazing. Ernest Schroeder, a follower of William Stanley Jevons, getting a handle on the consequences of any logical premises, or at least the fastest method for obtaining these consequences, seems to be one of the noblest, if not the ultimate goal of mathematics and logic. He said this is the most fundamental question in mathematics and logic. And the problem was kind of open for many, many years until in the early 70s, Cook independently Levine proved that it's NP complete. So it's still open, except at least we now understand it's NP complete. Okay, what does NP complete mean? So we know that P versus NP is one of the most outstanding open problem in computer science, or definitely the major open in theoretical computer science. Even mathematicians accept that this is a major open problem. It's considered a millennial problem with $1 million prize on solving it. And it's about computational complexity, how hard it is to solve computational problems. So you can trace the origin of computational complexity already to the 19th century, when people start looking at problems on graphs. So what is a graph? A graph is also called a network. You have a set of nodes and a set of edges between them. And there are two notions of cycles on graphs. One is called Hamiltonian cycle, a cycle that visits every node exactly once. And the other one is Eulerian cycle that visits every edge exactly once. So if you're given a graph, how hard it is to find Hamiltonian cycle or Eulerian cycle. Now, Eulerian cycle problem is really important problem because that's the beginning of graph theory. Now, what does it mean hard? We look at the size of the graph in, let's say, the number of nodes plus number of edges. And we want to know, can we solve it in, does it scale moderately? What does moderately mean? Polynomial, n to the c for some c. Many problems can be done. Is a number even? Yeah. Check the least significant digit, and so it's very easy to see that you can solve it very quickly. Is a number square? Can you solve it in polynomial time? To do that, you have to do what's called long square roots, which I still was taught in high school, but today I don't think they teach it anymore. But if you go and you read about long square root extraction, you see it's polynomial. What about Eulerian cycle? So Euler proved in the 19th century an easy actually lemma that a graph has Eulerian cycle if and only if every node has an even degree, because you have to enter and leave every node. So you can check it in polynomial time. What about Hamiltonian cycle? Can we do this in polynomial time? If you do a naive search, just all possible cycle, this will be n factorial, very, very slow. You can be a bit smarter and do it using dynamic programming, start with a Hamiltonian path and keep concatenating them. Then you get it to 2 to the n, which is much better than n factorial. Still, imagine you have a graph with 200 nodes, and so you need 2 to the 200 operations. And suppose you can do each operation in one Planck time unit, which is the shortest possible unit of time according to quantum theory. The universe is younger, much younger than 2 to the 200 Planck time units. So this is the question, can we do better? It's Hamiltonian cycle in polynomial time. Now, a key observation was made in the early 70s is that if I give you an alleged Hamiltonian cycle, if I give you I said this is Hamiltonian cycle, you can check it very easily. You have to check that between every two nodes, you're walking on an edge, and you visit every node exactly once. So checking is easy. Turn out there are many, many problems, thousands of problems where checking is easy. For example, factoring. If somebody gives you the factorization, you multiply the numbers, you check the factorization. So this is called NP. The name is not the best name in the world, in my opinion, but a better way will be easy checking, but EC maybe, but the name is now NP, and it means easy checking. So tens of thousands of problems have easy checking, including protein folding, for example. So the P versus NP is almost a philosophical problem. Is discovering solution really is it harder to discover a solution than it is to check solutions? So NP, we know how to check efficiently. P, we know how to solve efficiently. Are they different? And this is the question. Is checking really easier than discovering? Now, of course, intuitively, it seems that's the answer. In fact, we use it. We talk about finding a needle in the haystack. Finding the needle is hard. But if I say, here's the needle, stick your finger, get pricked, you know the needle is there. everybody knows that solving Sudoku is hard, but checking Sudoku is easy. We all know that much easier to read mathematical proofs than to come up with mathematical proofs. So many years ago, I was a researcher at IBM, and the lab director was a physicist. So he asked me, you all believe that P is different than NP? I said, yeah, this is the common belief. So he said, why don't you just accept it and move on, which is what physicists would do. I said, I had to come up with an answer. I said, if we don't know how to prove that P is different than P, it means we do not understand it. We are seeking an understanding. We don't really hope to show that P equal NP. We hope to understand why P is different than NP. So if P is different than NP, what are the implications? On one hand, many important problems cannot be solved efficiently. On the other hand, RSA encryption depends on the hardness of factoring. If P equal NP, then it will be easy to factor because you can just guess the factorization. So if we don't prove it, we cannot understand it. There's also the possibility that maybe, who knows, maybe the KGB proved that P equal NP, and they break RSA and they're reading all of our messages. So we would like to know that this cannot be done. Now, is it possible that P equal NP? Possible, but not very likely. Scott Aronson wrote, if P equal NP, then the world as we know it, the world is a very different place than we usually assume it to be. There's no special value in creative leaps, no fundamental gaps between solving a problem and recognize a solution once it is found. Everyone who could appreciate symphony would be Mozart. Everyone who could follow step-by-step argument would be Gauss, excuse me. If P equal NP, the good news, we can solve many important problems efficiently, but RSA encryption is not safe. Is it possible to P equal NP? Yeah, it's possible. While everybody believes that P is different than NP, it's still possible it's equal. It will require a very clever algorithm. But linear programming, now we know it is in polynomial time. It took 40 years to come up with the algorithm. Now, in the NP complete problem, like Boolean satisfiability, are the hardest problem in NP. And in 72, Karp showed that many other problems, like Hamiltonian cycle, is NP complete. That means that P equal NP only if and only if Hamiltonian cycle is in P. So we can focus on specific problem and try to show that they are in polynomial time. By now, there are thousands of NP complete problems. It's enough to solve one of them to show that it's in P, to show the P equal NP. For some reason, Hamiltonian cycle is a very popular problem to try to prove that P equal NP. There is a website for all the incorrect proofs that have been published that P is equal NP or P different than P. Hamiltonian cycle is a very popular problem there. So a very quick brief history. So in the starting actually in the 50s, already people tried to show that certain search problems are difficult. It started actually in the Soviet Union. It was known as the Peribor problem. In 1971, Steve Cook showed Boolean satisfiability is NP complete. Karp followed up by showing that many other problems are NP complete. Independently, Leonid Levin discovered the concept and proved that several problems are NP complete. By the late 70s, there was a famous book by Gary and Johnson, Computer Intractability, popularized the concept. And by 2000, a $1 million award was announced for this problem. On the other side, there have been people who just says, we just want to solve Boolean satisfiability, maybe not in polynomial time, but as efficiently as we can. And this goes back to 1955. Newell, Shaw, and Simon wrote a program called Logic Theorist to do Boolean reasoning. This was followed by a paper by Davis and Putnam in 1958, Davis and Putnam in 1960, and then Davis, Logeman, and Loveland in 1962. And this paper together gave rise to what's become known as DPLL, Davis, Putnam, Logeman, and Loveland. And it is one, convert the formula to conjunctive normal form. So the problem we saw here, this is conjunctive normal form. It's a conjunction of this junction of positive or negative variables. Then we just run backtracking search. And there's one heuristic which is if one of the clauses, the conjuncts are called clauses, the disjunction are called clauses. And if a clause has only one variable, then there's no, it means it's a degenerate clause, there's no order. Then you must, if you just like, if you have a clause say x2, then there's no need to branch anymore. X2 must be true. If it says not x1, x1 must be false. So this was DPLL. And DPLH was a standard method now for the next 30 plus years. And there was not much progress in the field. By the early 90s, we could solve problem with a few hundred variables. And if you said that's not good enough, people said it's NP-complete. What do you expect? And then in the mid 90s, the SAT revolution started. And a whole bunch of new heuristics, they're all heuristic, new heuristics, people start investigating heuristics, and many new heuristics were added. The key heuristic are, one is back jumping. When you do backtracking, you go up one level at a time. But if you're smart, you can jump back many levels at a time. So that's save you time. I mentioned unit clause. How do you detect unit clause fast? Smart unit clause preference rule. When a particular branch of the search fail, analyze why it failed, and don't repeat the same mistake again. Even making the choosing which variable to branch on. You have to choose a variable to branch on. You want it to be a good choice, but also you want to do it fast. So good choice heuristic. Sometimes it turns out just something, if you do a search and after a while you say, I'm going up and down, you said, okay, you know what? Let's just restart. Let's just restart the search. And that can sometimes work well. The first tool along what's called CDCL, conflict-driven closed learning, was grasped in 1966. Schaff came up in 2001 with smart unit clause preference and conflict-driven and smart choice heuristics. And the field has exploded, but now we solve problems with millions of variables. One huge mistake, in my opinion, to call it CDCL. Who knows what is CDCL? We should have called it deep solving with a deep voice. Just as an example of how much progress was done, this is from 2012. And a colleague of mine, Sanjit Shesha, decided to benchmark 12 years of such solvers on the same problem on the same machine. And he showed that the problem that they took in 2,800 seconds went down to 1 second in 2012. And so we had 3 orders of magnitude improvement over just over a decade. And the progress continues. People call it Moore's law for such solver. We're still making huge progress in such solving. And the progress has been so dramatic that at the beginning of the previous decade, people says we can use it now for industrial applications. And Leonardo De Mura and Nicola Bioner had huge success in doing it in Microsoft Research, but for industrial software engineering, all kind of things, symbolic execution, model checking, static analysis, modelless design, and so on and so forth. So today, such rolling is an industrial reality. And so the challenge that I think we are all facing is in neuro-symbolic reasoning, how to combine logic with machine learning. That to me is what neuro-symbolic reasoning is. Neural reasoning, machine learning, and symbolic reasoning. Now, I want to talk about what I have done along this line, which is not so much on the neural side, but to me, an important step is we have to make logical reasoning quantitative. Why? Because neural nets are quantitative. They compute weights. They compute probabilities of what, the LLM work by giving you what is the highest, most likely word to extend a sentence. So we have to take logical reasoning from being purely qualitative to quantitative. I actually start doing it from another industrial application, which is verification of hardware and software systems. Okay. Can I move these things? No. So hardware industry is a huge industry. It's close to $1 trillion a year. And everybody that works in industry will tell you that designing system, hardware or software, is the easy part. The hard part is to ensure that they meet they satisfy their intended functionality, verification, functional verification, or validation. So you wrote a program. Does it do what you wanted it to do? You design a chip. Does it do what you wanted it to do? And the estimate is that this takes about 70% of the development effort is validation, not design. Now, I spent much of my career on formal verification, which is try to do such validation mathematically and algorithmically. But when you talk to people in industry, it turns out, yes, they do it. It's a huge success, but it's less than 10% of the verification effort. What are the 90% being spent on? On what they call it, the nice name is dynamic verification, but it is really is testing. You simulate the system under different testing scenario, and you check the result. This is probably how you verify your own programs. You run it on well-chosen inputs where you know what the answer is going to be, and you compare. This is today, dynamic verification is today the dominant approach. People write what's called test vectors. There are inputs to the problem. And the test vector represent different testing scenarios, different verification scenarios, and then you compare the results. The question is, how do you generate many different test vectors to cover many different scenarios? The test space can be very large. Think, for example, one of the most famous bugs ever, the Intel floating point division bug. So imagine you want to do careful testing of floating point dividers. If you're dealing with 128-bit floating point numbers, there are 2 to the 56, 2 to the 256 possibilities. You cannot test them all. The sun will definitely go nova before this is done. So how can we really do good testing? So the classical approach that a verification engineer will read the documentation and will write by hand good test vectors covering different scenarios. The problem is this is very slow. It's like writing code. The conventional wisdom is that you can write 20 lines of code per day. So Verify can write maybe 20 good test cases per day. So this is not scalable. So in the mid-90s, people at IBM Haifa, Lichter, Malka, and Aharon developed a different approach. The verification engineer doesn't write explicit test vectors. Instead, they write constraints that describe scenarios, problematic input areas. And then we use constraint solvers to solve the constraints, and we use the solution as test vectors. And we rely on the progress with deep solving. Now we can have solver that they can solve large constraints. This has today become the dominant approach today. This is the de facto industry standard today. Right? Constraints, solve them, these give you test cases. But we don't want the solution, the test case depend on the internal of the solver. We want solutions that are random and uniform. Why random? Because we don't know where the errors are. Why uniform? Because if we cannot have any preference, we should be able to check everything uniformly. So this gave rise to a very simple, but to me, very beautiful problem. You're given a Boolean formula, and you have a solver. You have like mini-SAT. You have a very good SAT solver. But what you want to do is to generate solution uniformly at random while scaling to industrial size problem. So you want to get uniformly random solution to Boolean satisfiability. Turn out that this has many applications. One I just mentioned, constraint random test generation. Another one that I like very much, when people start popularizing MOOCs about around 2012, they discover you can have a course, it gets taken by tens of thousands of students, and you want to give them homework. But there are discussion forum. If you just give everybody the same problem, people will post solutions on the discussion forum. So how do you generate 50,000 different problems? The answer is you parameterize, you create parameters in the problems, you write constraints about the parameters, And now you generate uniform, you generate solutions uniformly at random, and you can generate 50,000 different problems. But there are other applications as well. Turns out that this problem of uniform random generation was a classical problem in theoretical computer science. The first paper on this was 1986, and this was Jerome Valiant and Vazirani, and they show how you can do it with a randomized polynomial time algorithm with a sigma P2 oracle, an oracle in the second level of the polynomial hierarchy. A few years later, Bellari, Golach, and Petrank show how you can do it with an NP oracle. Why is that important? Because NP oracle is a SAT solver. SAT solver is an NP oracle. So in 2011, with a student Kuldeep Mill, we implemented the algorithm, and we discovered it did not scale above 16 variables. So it was a nice theoretical solution, completely non-scalable. Remember, at that point, we're already solving problems with tens of thousands of variables. So, or even 100,000 of variables. So 16 was a joke. So we had to go back to redo the theory to get scalability. And the first thing we did, we said, you know what, let's compromise on uniform. Let's make it almost uniform. And I will explain. So we're able to do almost uniform generation, randomized polynomial time algorithm with a SAT oracle, SAT solver. And we use universal hashing, which I'll explain. We use SMT solver, I'll explain. And by now, this method, Unigen, scaled to millions of variables. So we had to redo the theory to get scalability. So first, what is almost uniformity? So suppose you have a formula phi, the solution space is solo phi, and suppose there are kappa solution. Uniformity means that every solution comes out with probability 1 over kappa. Almost uniform means that you give me a parameter epsilon, and the probability will be 1 over kappa within a factor from above and below of 1 plus epsilon. So it's almost uniform, which in practice, it means it will be good enough. So how do we do it? Here is how we do it. We take the solution space and we partition it into roughly equal small cell of appropriate size. Then we choose one cell at random. We enumerate the solution in that cell, and it's going to be a relatively small number of solutions, so we can enumerate them. And then we select one at random from this cell. And because the cells are almost equal, roughly equal, this will be almost uniform. But now the question is, we have a space that we know nothing about the solo phi. How do we partition it into roughly small equal cells? We don't know the distribution of solution. Here comes a beautiful idea, universal hashing, introduced by Carter and Wegman in 1979, and then investigated further by Sipser and other people. And it's a beautiful idea. So if you go back to Knuth, I think it will be in volume 1 even, hash function map a large space to a small place, to a smaller space. And a good hash function would take, if the inputs are randomly distributed, then you'll get good distribution, uniform distribution of the outputs. But if the inputs are not well distributed, some crazy distribution, then we know nothing about the output distribution. So the idea of universal function is you have a family of such function, you choose one at random, and this will randomize over an arbitrary distribution of the input. We know nothing about the input distribution. We choose a hash function at random, and then the outputs will be almost uniformly distributed. So we'll get the cell will be roughly equal in expectation. So this is the idea of universal hashing. We'll see how we implement it. Turn out we need a little more. We need to when we do probability analysis, we need to be able to independence to multiply probabilities. Now, a universal hash function may not give us independence, may not hash different inputs independently. So there's a concept of R universality, and it says if you have R inputs, they will be mapped independently. And the bigger the higher the larger R, the more independence we have, and we have the bigger guarantee on the distribution of outputs. And there are ways to get R universality. You need to use polynomial of higher and higher degrees. But the higher universality means because higher degree polynomial means higher complexity. So Bellaire, Goldbach, Petrank, they wanted full uniformity. So they went from N universality. But that means they had to deal with very high degree polynomials. We show that if you do 3 universality, which is much easier to obtain in practice, then we get almost uniform generation. And that was the key to improving the scalability from tens of variable to millions of variable, going from N universality to 3 universality. Now, in practice, it's actually relatively easy to do. How do we want to take the whole space of 0, 1 to the n, all the truth assignments, and partition it into 2 to the m cells. So we create random XOR constraints. What is a random XOR constraints? It's a sum. The sum is going to be, it's a modulo 2 sum. The sum is 0 or 1. You choose randomly 0 or 1, but you put a variable in the sum or not with probability half. So you get such an equation. And if every such equation split the solution space in half. If you have m such equations, then you have 2 to the m cells, and we can make m large enough so the cell will contain a small number of solutions, and therefore we'll be able to enumerate them and choose one at random. But now each cell is described by a conjunction of CNF and XOR clauses. It's not just CNF, CNF plus XORs. Now XORs by themselves are easy to solve. They're just linear equations. You can do just Gaussian elimination modulo 2. But combining CNF and XOR is non-trivial. And here we had to use SMT. So what is SMT? SMT is satisfiability modulo theory. And this is how to combine Boolean reasoning with another type of mathematical reasoning, for example, linear constraints, or in our case, XOR constraints. In 2000, people said, let's leverage the progress in such solver to do SMT, huge progress since then. And in 2009, Mate Seuss developed a solver, he called it Crypto Minisat, which was combination of CNF and XOR, is a clever combination of such solving with Gaussian elimination. And he intended to use it for an analysis of cryptographic protocol. It was not necessarily a huge success there, but serendipity, we discovered a solver, it was exactly what we needed. So we developed a tool based on this theory. And first of all, we want to see how good is almost uniform sampling. And we developed for a problem with we took a particular problem with million solution. So we developed an exact sampler for this, a uniform sampler, and we compare it to the almost uniform sampler, and statistically they're indistinguishable, really indistinguishable. So the almost uniform was very good. That's one thing. The other question was performance, and we compare Unigen to what was then the best sampler at the time, which was called XOR sample prime. And XOR sample prime was the best effort sampler. We're trying to be as uniform as we can, but we give no guarantee. We give guarantee, almost uniformity, and we were still 2 to 3 order of magnitude faster than XOR sample prime. The success convinced us to go into really the most fundamental problem in quantitative reasoning, which is counting. Given a formula phi, how many satisfying assignments does it have? This is known as sharp-SAT. Sharp-SAT is complete for sharp P, the class of counting problem introduced by Valiant in 1979. Now, there are many applications. I mentioned the consent random. Consent random, you want to know, before you start generating random solution, you would like to know, okay, how many solutions are there to estimate what kind of coverage you have. But the killer app for constraint counting is Bayesian inference. Bayesian inference is known to be equivalent to constraint counting. That's what you have to do. There are solvers for sharp-SAT, but SharpSat is much, much harder than SAT in practice. So in SAT, we solve problems with millions of variables. For SharpSat, exact counting, tenth of thousands of variables is the best we can do. So we said, let's do approximate counting. Now, again, the idea was not ours. This PAC was popularized by Valiant, but was introduced by Stockmeyer in '83. And for any kind of counting problem, and the idea is you're trying to do some counting problem. Exact, you get a precise count. Approximate means that the count within a factor of 1 plus epsilon from above and below. And the probably is you introduce randomization and you want to get a good result with probability at least delta. So you have two parameters. Epsilon is accuracy and delta is the confidence. And again, in 1989, Jerome Sinclair and Valiant showed that approximate counting is in BPP to the NP, so randomized polynomial type with NP oracle. It has not been implemented, and we know if we implement it directly, it will not perform well for the same reason with Bellari, Goldbach, Petrank. It will not perform well at all. So we took the sampling technique and extended it to counting. And so again, we use these XOR clauses, and then we select a cell at random. Now we count the solution in the cell, multiply by 2 to the m, because there are m cells, there are 2 to the m cell, we get an estimate, and we iterate until we get the desired confidence, and we get a method, approximC, which is a polynomial in the formula in 1 over epsilon and in 1 over log of 1 minus delta relative to a SAT oracle. This is how many SAT solver calls you're going to make. We compare it to, at the time, to what was then the best exact solver, which was Cache, exact counter. We chose epsilon to be 0.75, and we showed that we still got about 5% accuracy. So it was it was better than we expected. And the performance is more nuanced picture now. On small problem, Cache was faster. But Cache timed out about 50,000 variables, while approximC was able to scale to hundreds of thousands of variables. So on small problem, the answer was run Cache, but if Cache does not solve it in 5 minutes, forget about it. Just switch to approximC. So I just want to give you a kind of, it was a very quick tour on partly, I think, what we need to do to reasoning to be able to integrate it with neural reasoning. This is just the first step. There's been follow-up work by Kuldeep Mill, my ex-PhD students, on how to use, for example, approximate counting to reason about neural models. That's an example. So my thesis is that it's a paradigm glide, not paradigm shift. Data-driven CS, refined model-driven CS, does not replace it, just as physicists still teach classical mechanical automatism optics. But we have to bridge the gap between machine learning and logic to get a human-centered AI. On the other hand, there is, I claim, a paradigm shift, but it's not technical. You have to look at the bigger picture, the political picture. So this is very much US numbers, but in 2024, NSF budget for research budget for computing was $1.5 billion. Now this is just NSF, but it's well known that NSF funds about 80% of all academic CS research. On the other hand, in April 24, the news, Google will spend more than 100 billion on AI, exec says. So it's not all research, but still $1.5 billion is a drop on the bucket for Google. And this is just one company. So clearly the center of gravity of computing research in particular in AI has moved to big tech. It's not in academia anymore. Now, does it matter? I claim that it does matter. Why? What is the purpose of academia, you should ask? And I think the best answer to that, I saw AAUP, American Association of University Professor, in 1940, the famous statement on academic freedom. And the rationale why we need academic freedom is, first of all, the rationale for universities. And they wrote, institutions of higher education are conducted for the common good. ACM Code of Ethics. Computing professionals' actions change the world. To act responsibly, they should reflect upon the wider impact of their work, consistently supporting the public good. My goal when I do research is to support the public good, the common good. But we all know that that's not how big tech operates. It's all about money. And I wrote an anguish essay in January of 24, Computing with Blood on Your Hands. And I spelled out, really, literally, we have blood in our hands. But in fairness, I took responsibility for all of us, but it was all about on the industry. Okay, we are involved in it because we are producing the students go to industry, so we cannot be fully exonerated. But the pursuit of profits now trumps the common good. There's no question about it. And a nice example is what happened with OpenAI. It was established in 2015 as a non-profit. They discovered there is one problem with when because they really wanted to be open and to do good. They wanted to do good, the people that established OpenAI. Then they realized the problem, how to attract investment for non-profit. So they established a for-profit subsidiary. So the for-profit will attract investment, but the non-profit board will stay in control. And then in December of 2022, they launched ChatGPT, and that's the world that changed since then. Within a year later, the non-profit board fired Sam Altman because he thought he was focusing too much on growth and on safety. But then all the investors put tremendous pressure on them, and that became a battle between big good intentions and big money. And guess what? What a shocker. Big money won. And within 5 days, Sam Altman was reinstated. So big money dominates big good intentions. So let me conclude. We had really revolutionary progress in machine learning. We also had not so well known, but revolutionary progress in automated reasoning. I think the reports on the demise of formal CS are greatly exaggerated, but the center of gravity of computing research, especially in AI, moved to big tech. That is a problem for all of us. Thank you very much.
Thanks so much for that. Amazing talk. Yeah, you can see the claps going up. If people want to put questions, please do so in the chat. While people are thinking of questions, Moshe, I had two things that I thought I would ask you. I'm sure you've been thinking about this already, so maybe you have an answer. So on the technical side, a very nice segue into model counting. I suppose, the argument, and I'm not saying I believe this argument, but I can imagine those members of the machine learning community who are less familiar with combinatorial problem solving using discrete techniques might feel, well, these constraints, sure, they're important, and maybe there's a narrow set of domains where they become very important, but yet we are seeing instances of some kind of constraint solving in practice. I'm not saying it matches in any way, shape, or form the kind of rigor and breadth we have in discrete mathematics. But they might say, for instance, sure, there are a few Tesla crashes, but largely it seems to work. And obviously, there are constraints that the Tesla and other self-driving cars are dealing with. And again, I'm not talking about the horror stories, right? And there are many of those, but largely they seem to function. So why should we bother with it too much? Maybe it's a niche area, and maybe over time, there will, in fact, people who work on discrete mathematics might come over to our side, bringing ideas with them that might translate to our language, and ultimately these models will get safer. So that's on the more technical side. On the more philosophical. Okay,
Let me
yeah,
try to first answer that. So
yeah.
I'm not saying that we should all drop machine learning and go and do model counting. This is really in some sense a call for action. Said we have huge progress in reasoning. We have made progress to make it quantitative. We need to, I don't have a solution. If I had a solution, I would give you a talk how I integrated neural and symbolic reasoning. I don't have it yet, unfortunately. But a lot of smart people here, and I want you guys to think that, to me, it was an important step is to make logic, first of all, more quantitative. I don't think if it's just purely qualitative, then there is what I call impedance mismatch. I
Yeah,
think we made progress, and now we can try to think what is a good way. There are lots of proposals, there are different proposals how to do neuro-symbolic reasoning. It's a very dynamic field. And all I'm trying to say is that I think quantitative reasoning offers us kind of opens a new door to the integration, but what shape the integration will take, I do not know yet, okay?
fair enough.
Uh, whether it's a niche area or not, time will tell. Just to remind you, there is a story from a colleague of mine who went to NURIPS in 2000, where it was still called NIPS in 2000, and there was a reception, and he saw Jeff Hinton in the reception standing in the corner. No one wants to talk to him because he is the only guy that still believes in neural nets. This was at NURIPS, okay? And Jeff
Yeah,
Hinton was the only guy in 2000 that still believed in neural nets. So at that point, neural nets was a niche, okay? And look at it now. So I
yeah,
would say, history will judge what
yeah.
is a niche
Great.
and what is not a niche.
Yeah. I don't know if you can see the chat, Moshe. There's
But
actually a
you had a
question from.
you had a second question there. I
Oh, I did.
interrupted
Yeah,
you.
I'll come to that. I just realized that there's one chat by Swaroop. In fact, he has a kind of similar question, I would say, but it's maybe more directed at the approximate counting technique you presented. So he's asking, how would we relate this to approximate correctness of the outputs of LLMs? I think you're kind of hinting that once you understand the quantitative story, maybe we can link it to that.
So there is some work that have already connected LLMs to graphical models. Not LLMs. I mean, I'm jumping ahead of myself, but not LLM, but just neural nets.
Yeah.
Taking neural nets and interpreting it as graphical models. So, again, with neural nets, again, not LLM, but neural nets, I don't think we should assume now that machine learning is all LLMs. There are lots of applications of neural nets that are not in the language area and not generative, in fact. But
Mm,
can we use? I mean, there are two costs there. There is a training cost, and then there is what's called inference cost. Okay, if you want to apply it, inference cost. Can we use techniques from here to speed up the inference cost, for example? Okay, I'm saying what I'm trying to say here that we should think broadly rather than narrowly. Okay,
yeah.
we have had huge progress in symbolic reasoning. I'm completely unideological about this research. Whatever, to me, whatever works. Okay, if somebody can show that neural nets can do better reasoning, I said okay, just convince me. But right now it's not there yet. Okay,
Yeah.
and so I think we have two success stories. One is very well known. The other one is more technical and not so well known. So I'm trying to popularize it and say, guys, let's ride on the success. Let's ride on the shoulder of giants, and let's ride on the success of both types of reasoning.
Very nice, Moshe. Let me ask you the other question I had, and then we can. I'm factoring some of the other questions that came in the chat. So regarding your more political point, I suppose again, if I'm thinking from the point of view of an early career researcher, they work in computer science. I don't know how things are in terms of funding for theoretical computer science in the US, but in the UK, I would say largely it's underfunded, right? So the majority of the funding is very AI centric. So if you think about the perspective of an early career researcher, they're getting into this field, maybe they got themselves an academic position. Now they need to grow their lab, they need to bring in funding, and of course the temptation is to convert and link up to what the big tech is doing, right? Because that's the way, on the one hand, you can garner interest from those companies but also show to the funders that look, what I'm doing is industrially relevant. So taking into account, we need this academic infrastructure understandably, and it holds a special place that I agree with you that, big tech is somehow completely suppressing. How would you say this early career researcher should, working against these waves, so to speak?
So in certain on certain things like that, the individual very often powerless, but we have power as a collective.
Hmm.
Okay, and we kind of have to to kind of to fight back these ideas. Or industry will do all the research.
Right.
So in fact, one thing we're doing at CSCM, we are producing a special issue on federally funded research, and where we went to, not exclusively, but to lots of Turing Award winners, and some people have produced kind of very significant research, very impactful research, and said, tell us the story. How federal funding or government funding in general, this was very, I have to admit, this is very US centric, but how federal funding has enabled you to do world changing research.
Hmm.
And the answer is that one of the things that you have, I mean, you have in academia, you have two advantages. Okay, one is you can really think about the public good, and the other thing, you can think long term. Okay, and in fact, we would not have today the progress we have in AI if we did not have academia to support. Because think about Pitts and McCullough write the paper on neural nets in 1943. Okay,
Hmm.
it took only in, kind of the deep learning revolution started like 2012.
Yeah.
So the answer, it took 70 years.
Hmm.
I mean, it's if 70 years, I would say it's even like maybe at least three academic, if not four academic generations. Okay,
Hmm.
so this idea, oh well, I can work now and there will be something next year, it will be out. Yeah, certain things work like that, but other things, it takes decades. Okay, in my own research, if you look at a model checking, so again, you can go and you see decades of work. Much of it started by, somebody introduced automata on infinite words.
Hmm.
And what can be more esoteric than that? Automata on infinite trees. What can be more esoteric than that? Okay, and
Hmm.
then you end up some decades later with industrial products.
Hmm.
And
Very
so
nice.
I so we are producing a special issue. It should come out already. Many articles are available on the web, and they're all, wow, look at that. We would, GPUs. I mean, GPUs. How did it start? Again, it started from government funded research on. Remember, it was video games. Remember how we got to GPUs. It was all for video games. Okay, very
Hmm.
few people took it seriously. Suddenly realized, oh my goodness, this can do matrix multiplications in parallel. Wow, we can use it for to train neural nets. Totally unexpected.
Yeah. In the interest of time, Moshe, I'll try and summarize some of the other questions that were asked. Let me just ask them. I think I could probably think of three ways of putting together these thoughts. One of the question particularly relates to, and I think you're probably suggesting this in your talk anyway. If you see alpha proof, I mean, it's definitely a neurosymbolic approach of things. So I guess the question is, how do you see that as a beneficial trend in the long run? This idea that you might use certain things with symbolic solvers and certain things where language models might do well. So that's one question. If you prefer that answer them individually, that's fine too.
Yeah, let's answer them
Uh,
individually.
okay,
I,
yeah.
I think this is very much, to me, should be the cutting edge of research. We kind of integrate. Look, I mean, look at us. Okay, I have a neural. I mean, it's first of all, it's all neural. Even the symbolic is implemented top of neural. Okay, but we still understand that the way to understand how we think rationally is not at the neural level, but at a higher level. Okay,
Hmm.
but at the same time, our lizard brain, we
Hmm.
know how it works. It's just a neural net. Okay, when I see Jessica's face here, I say, oh, we met at Rice. I recognize her immediately. I don't have to go and do an analysis about the hair and the eyes. I just recognize her. It takes me half a second to say, oh, yeah. We met at Rice, okay?
Hmm.
Hi, Jessica. And so this is fast thinking. And that's, I said, it's amazing to me. Daniel Kahneman wrote it in 2011. A year later, we have AlexNet and all these things start, okay? But we integrate it seamlessly. I don't, when I kind of operate in the world, I don't want to think, okay, this is now my forebrain talking, and this is my aft brain talking. You know, we don't think this way. It's a seamless integration. Nature has done it. You can integrate it. So now we need to figure out how to integrate these two different modes. That reasoning, I said, there are two modes of reasoning, neural and symbolic. How do we integrate them? That to me is right now. That's why the neuro-symbolic approach to me is makes eminent sense. We have two
Hmm.
success stories. Let's build on them. Let's find a way how to integrate them in a way that we get that the sum should be more, the whole should be more than the sum of the parts.
I wonder if you could contrast that with, I don't know how familiar you are, Moshe, with AlphaFold, which is the protein folding,
Yeah.
which was cited in the Nobel Prize. And now in AlphaFold, as you might know, there are some issues of constraints. There are geometric constraints. There's also quite a bit of background knowledge, but the entire pipeline is largely differentiable. They might argue. Even Google DeepMind's white papers sort of differentiate in a way, calling alpha proof quite neurosymbolic explicitly, whereas AlphaFold is kept as a kind of differentiable solution that has these things baked in. I wonder if that's a distinction worth thinking about, or or does it go back to your point that time will tell which one is more robust and rigorous in the long run?
Look, a student of mine, Jiwei Zhang, just finished his PhD about less than a year ago. And his PhD, part of what he did his PhD, is develop a SAT solver that is based on continuous optimization. So you take the problem, the discrete problem, you map it to a continuous domain, and then you use gradient descent to solve the problem. Okay, so just because you start with something which is discrete, it does not mean that you have to use discrete techniques to solve it. So right now we're not competitive. We're not competitive with a state-of-the-art SAT solver, but we have an advantage. So state-of-the-art SAT solvers require they're very much based on CNF. You add just XORs, and you have to spend a lot of work to be able to do it. GWAS techniques are more general. You can deal with different type of constraints seamlessly because they all map. We have this kind of way to map them to the continuous domain. So it has other
Hmm.
advantages. And in this case, we did really symbolic reasoning, but
Hmm.
inspired by the success in continuous optimization in neural reasoning. So
Hmm.
the technique. I'm not just saying I will bring technique to. I'm so smart. I will tell the neural people how to do better. No, I'm also learning from them and bringing
Hmm.
in some sort of neural techniques into the symbolic world.
Yeah,
Okay.
John Hooker, I think many years ago, was trying to also look at the interplay between optimization and SAT and how you could solve one with the other. One last question, I think, just in the interest of time. You mentioned the historical origins of Boolean reasoning, and going back, even Leibniz, for instance, talked about the idea that maybe you could come up with an algebra for thinking. Now, to some extent, most of these logics, going back to these philosophers, they were trying to capture what they felt was certain procedural ways of thinking, which they felt these logical rules capture. But to some extent, we could argue also that all of these logics haven't quite captured all the subtlety of natural language. So if somebody like Jeff Hinton were to come along and say, and I think he has been saying this, but if he were to come along and say, I'm training these large language models, they're capturing exactly the approximations that is implicit in human language and conversation, why would we need a logical foundation at all?
Well, you should pose this question to Aristotle in some sense, or even to Pythagoras, because if you look, this is kind of one of the most amazing, I think, kind of, if you look, what has humanity done, which is amazing things by humanity. One is development of language, okay? And, the wolf would say, who needs language? We get along very well without language. What do you guys need language? But we think language is an amazing progress, okay? But then from language, we got mathematics, because somehow by abstraction, right, we discovered that the plurality can be independent of the context. Okay, so we're
Mhm.
talking about two monkeys and two bananas, then the two is independent of the monkeys and the bananas. So we have a concept of two, okay, and then
Mhm.
three. And so we discover the concept of numbers. So
Mhm.
we start thinking quantitatively. um, I mean, we find there's something called Lemombo bones, where you see somebody was counting, doing notches on a bone. We don't know what they were counting, but they were counting something. Okay, maybe
Mhm.
the days of the month or something like that. But then the Greeks made another amazing discovery, which is deductive reasoning,
Mhm.
that the language is imprecise and we need to constrain it in order to get at what we call mathematical truth. And this goes back to um, Pythagoras, or even before Pythagoras. People developed the deductive method. Um, why are we teaching students today in high school plane geometry? Now, it's
Mhm.
been there for so long that people forget what is the reason. The reason is not that geometry is important. It should be a course in deductive reasoning. That's what's important about plane geometry. Because you're showing someone a language is very imprecise. But if we constrain it and harness it in a particular way, then we get this amazing thing. We get proofs, which has been called the
Mhm.
high road to truth. Okay. And Jeff Hinton may be willing to abandon that. I'm not. I still think
Mhm.
that mathematics is one of the highest contribution of humanity. You know, we invented mathematics. In fact, we
Mhm.
cannot imagine, we wouldn't have neural nets if we did not have mathematics. Mathematics underlines everything we do in science, okay? And I'm not ready to abandon mathematics to the imprecision of language, okay? If I want to write if you want to write a sonnet to your girlfriend, yes, use LLM, okay?
Mhm.
But now, there is now, of course, attempt to integrate it. People are trying to combine LLM with Lean 4 and to say how we use the generative a strength of LLM, and then
Mhm.
the constraining part of Lean 4 to make sure that what you get is a real proof. So we can innovate at the integration level,
Mhm.
but without putting the constraints of truth. Really, what are the constraints? The constraints are in the in the pursuit of truth. Language is imprecise by itself, not good enough by itself, and we've discovered it about 2,500 years ago.
Fantastic. Thanks so much, Moshe, for taking time. As I mentioned, we'll upload this video on YouTube and share it with you. But thanks again for coming today and taking time. And thanks everybody for attending. See you all very soon. Bye for today.
Thank
Bye
you
bye.
so much.
Thank you again for inviting me.
Thank you
Thank
for
you, Moshe.
coming.
Bye bye.